All right, in this lesson, we are going to talk about how to graph exponential functions using transformations. And so we're going to look at the parent function 2 to the x. There's also 10 to the x, there's e to the x, 5 to the x, 1/2 to the x, but we're going to focus on y equals 2 to the x right now. Okay, and so just to get some points that we can graph, if you plug in 0 for x, anything to the 0 power is 1. If we were to plug in 1 for x, 2 to the first power is 2. And then if we were to plug in 2 for x, 2 squared is 4. So we have the point 0, 1. We have the point 1, 2. And then we have the point 2, 4. So you may notice in the y column, they're doubling each time, times 2, times 2. And so whatever your base is, that's the common ratio or the common multiplier. If that said 3 to the x, I'd be multiplying by 3 each time. And so that means as I go backwards, I'm cutting in half. And so that would give me 1/2, 1/4, 1/8. And we keep getting closer and closer and closer and closer to 0. And so whenever you're approaching a certain value but never actually reach it, that's called a horizontal asymptote. It could be a vertical asymptote. We've seen those before. And so there's our horizontal asymptote at y equals 0. That's the number we are approaching. Okay, and so the other thing I want to point out is no matter what this base is, anytime we plug in 0 for the exponent, we're going to get 1, because anything to the 0 power is 1. And so 0, 1 will always be your y-intercept as long as there's no transformation. So 0, 1. Okay, and then your asymptote will be y equals 0. Domain is all real numbers all the time. We can plug in negatives, we can plug in positives, which shows on the graph. We're going forever to the left, forever to the right. Okay, and then range, we are strictly above the horizontal asymptote, so we don't actually equal it, but we're strictly above it. And so we are at 0 with the parenthesis going to infinity. It goes up forever. Okay, make sure you use that parenthesis, because if you use a bracket, you're going to say we're equaling the asymptote, and you can't do that. Okay, this function is growing as we go to the right, so this is increasing, and it is also growth. Okay, and so anytime you are moving away from the asymptote as you go to the right, it's considered growth. Anytime you're approaching the asymptote, that would be considered decay. All right, so now let's talk about if we have a negative x. On one side, we know that a negative right in front of the x is considered a reflection across the y-axis. We also know that we could rewrite that as 2 to the negative 1x, just separating the negative from the x. And 2 to the negative 1 power is the same as 1/2 x. Okay, and so that changes our base. Anytime you have a negative exponent, it's going to change your base to a fraction. And how that ends up looking on the graph is if I were to graph it, I'd still have 0, 1, but I would be cutting in half as I go to the right. So I would then have 1/2, 1/4, and then I would be doubling as I go backwards. And so 2, then 4, and so you can think of it as 1/2 to the x, or you can think of it as 2 to the x reflected across the y-axis. And so 1/2 to the x and 2 to the negative x are equivalent. Okay, and so that's going to be an important concept. When you see a negative exponent, you can change your base by just flipping it to the reciprocal. Okay, and so our critical point is still 0, 1. The asymptote is still y equals 0. Domain still all real numbers. Range is still above the 0. Okay, just because we reflected it across the y-axis, it's going towards the asymptote as we go to the right, but it's still strictly above it. And so the range is the same. Now it is a decreasing function. If we have a person traveling on this curve to the right, he is going down the mountain. Okay, and then this is considered decay. Anytime you are approaching the asymptote, you're approaching zero. Think of population as decaying, it's dying off. So that would be considered decay. Okay, and so now we're going to talk about all our other transformations other than just that reflection. We have a value in front. That's a reflection across the x-axis. If it's negative, it's also your vertical stretch and vertical compression. So reflection across the x-axis, think of that as your vertical reflection. You would be below the asymptote. So pay attention to that. Okay, and then B would be this value. Don't confuse that with base. B is your reflection across the y-axis, so that would switch you to decay. And then it is our horizontal stretch and horizontal compression. Okay, I want to mention, if you have a factor here, you can change your base by actually applying that number to the base, just like we did the negative. Effects of C, that's our normal left and right. If it's minus, it's right. If it's plus, it's left. Everything's opposite up there. And then D, the value outside the exponent, outside the base. It's completely off to the side. That's how you move up and down. Plus moves up, minus moves down, just like you would expect. Okay, and so the only transformation that actually affects the vertical, or there is no vertical asymptote, so there, right, none. There is no vertical asymptote here. The horizontal asymptote is only affected by moving up and down, and so that's going to end up being y equals d, whatever this up and down number is at the end. Okay, your domain is always going to be all real numbers. That will not be affected by any of your transformations. Range, that depends on whether you are reflected across the x-axis. So if A is still positive, this A value up here, if A is positive, it's still going to be from the asymptote to infinity. If A is negative, you're going to be below the asymptote, so you're going negative infinity to whatever that D value is. Okay, and so that horizontal asymptote should always show up in your range. Okay, the other thing that's helpful is to note you can make a table of points for any of your parent functions. Always use 0, 1, 2 for x. And so if our base is 2, we would have 0, 1. We would have 1, 2, 1, 4. So it's the base and then the base squared. If, let's say, our base was 3, we would still have 1, 3, and then 9. If our base was, let's say, 10, we had 10 to the x. I'm going to write the x with it so you know that's the base. If we were talking about 10 to the x, we would still have 1, 10, then 100. Okay, and so that's actually going to help us graph using transformations, because clearing off my graph a little bit, I want you to notice the pattern between the points. Your y-intercept is always a distance of 1 away, and then your second significant point to the right is going to be your base away. Okay, and if you wanted a third point, your next significant point, and I'm talking about distance from the asymptote. Okay, distance from the asymptote, 1 away, base away, and then the base squared away. Okay, and so that's how we're going to graph using our transformations. Okay, and so the last thing I want to do on this first page is just remind you of what all our transformation rules look like. A +5 outside the function would be outside your exponential expression. That would move you up 5. -5 outside the exponential expression is down 5. Now inside and outside the parentheses, now corresponds to inside and outside the exponent. And then remember, anything inside the parentheses, I call these the crazy house. Everything's backwards. So plus moves you left, and then minus moves you right. Same transformation rules. A negative outside the exponential expression, they probably won't have those parentheses, is going to be your reflection across the x-axis. And so then you're going to see your function upside down below the asymptote. And then if your negative was inside, that would be your reflection across the y-axis. Okay, this scale factor outside would be your vertical stretch by 5. And then if you had the 5 inside, that would be your horizontal compression by 1/5. Okay, and so we're going to start with some easy examples and then work our way to the harder examples. All right, in example number 1, the first thing you should do is identify the parent function. So our parent function here is 2 to the x. Okay, and so we are working with base 2. After you identify that, then identify your transformations. And so we have a left 5, and then we also have a down 3. Okay, and so once you've identified your transformation, start by graphing the horizontal asymptote. Because we're down 3, the horizontal asymptote is y equals -3. And then you know the domain is always all real numbers, and you know your range. Because there's no reflection in front, it's going to be above that -3. So you would go from -3 to infinity with a parenthesis. Okay, so to create the graph, just thinking of the parent function, your parent function has a horizontal asymptote at 0. And then, let me make that thinner, has a horizontal asymptote at 0. And then the significant points would be 1 away for the y-intercept. And then the next point would be the base away. In this case, it's 2. And then the next point from there would be 4. Base, then base squared. Okay, and so that's how I would create the graph. And then we've moved this left 5 and down 3. And so instead of graphing it here, we're going to want to create that pattern down at -3, where I said the horizontal asymptote was. So horizontal asymptote at -3, put that on your graph first. And then my 1 away point, my y-intercept, has been moved left 5. So instead of putting it on the y-axis, we're going to move it 1, 2, 3, 4, 5. There's my 1 away point. Okay, after you get your 1 away point, now do your base away. And so here's 1, here's the base, 2, and then base, or then a distance of 4. Okay, and so then you can create the rest of your graph, growing to the right, decaying to the left. Okay, for this next one, first identify what the parent function is. A lot of people mistake that 4 as a vertical stretch or one of your transformations. That is not a transformation, that's your parent. And so we are working with 4 to the x, which means we are base 4. That's going to affect our points and our distance from the asymptote. Okay, next we're identifying transformations. We have a reflection across the x-axis. We have a right 5. And we have a up 2. Okay, so that up 2 puts our horizontal asymptote at y equals 2, going ahead and filling in the domain. And then we do have a reflection this time. And so that means we are going from -infinity to the 2 for our range. Again, still with the parenthesis. Okay, and so when I graph this function, I'm going to start with the horizontal asymptote at 2. Get points for graphing the horizontal asymptote. Next, if nothing else happened, I would have a 1 away, and then I would have a 4 away. And then my next point would be 16, which is clearly off the graph. And so I'm just going to leave it at the 1 away and 4 away. And so this has been reflected. So now it's going to be 1 away and then 4 away underneath the asymptote. So these aren't here. And then it has been moved right 5. We've already taken care of the up 2 by graphing the asymptote. So now we just need to take these points and move them to the right 5. So no longer on the y-intercept, your 1 away is right 5. Right here at the 5. Okay, so always look for that 1 away point, the distance of 1 from the asymptote, to figure out how far it's moved left and right, and then do the base away. In this case, the base is 4. That's why we need to identify that we're working with base 4. Okay, that's also how you're going to write your equations from a graph, is identifying the distance of the points from the asymptote. And so that's why I like to graph this way. Okay, and so there's our new graph. Okay, on number 3, here you're seeing a 1/4 as a base. And so instead of working with a fraction, remember you can change the base. And so if I want to rewrite that as a 4, I would just need to put a negative on the exponent. Okay, and then copy down the rest of the function. Okay, and so I don't like working with fractions. I'd rather work with a reflected whole number. And so this is base 4. Okay, and so now when I'm identifying my transformations, I have a reflection across the x-axis. I have a vertical stretch by 3. I have a reflection across the y-axis. And then I have a left 4. And then I have an up 3. Okay, even though all of that has happened, the only thing that affects the horizontal asymptote is y equals 3. So just go to that number at the end to figure out what the horizontal asymptote is, and then you can go ahead and graph it at y equals 3. Okay? And then domain, all real numbers. And then because of the reflection, because that negative in front, we are going to have a reflected range. So we are going from negative infinity to that 3 with a parenthesis. Okay, and so now usually we would have a point 1 away on the y-axis, but let's keep in mind it's reflected across the x-axis, so it's down here. And it's also vertically stretched by 3. That's going to change my 1 away point to be a distance of 3 away. Oops, that was only 2. 3 away. So usually we would have 1, then 4, because our base is 4. Now we are going to have a distance of 3, then 12. Those distances get multiplied by 3. Okay, and so there's my 1 away point. And then my next point would be 12 away. Okay, and so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It fits. Okay, and so when I'm talking about distance, I'm measuring from the asymptote each time. Okay, not from the previous point. So my distances are 3, then 12. Okay, we've already taken care of the fact that it's been reflected because we're underneath it. We've taken care of the vertical stretch by 3. In order to take care of the reflection across the y-axis, instead of going to the right with this 12 away point, we actually need to put it to the left. Okay, that's going to reflect it across the y-axis. Okay, and then to take care of the left 4, we need to take both of these points and move them to the left 4. Okay, and then we've already taken care of the up 3 because we started by graphing the asymptote at 3, and that's what we've been referencing each time to graph these points. So now we just need to connect them. And so we are approaching the asymptote because we have exponential decay that's reflected below the asymptote. Okay, this last one, once again, there's a 1/2 here, so we can rewrite that as 2. We would just need to make our exponent negative. Now, if you're noticing, this exponent is already negative, so let's go ahead and distribute the negative just to make it look nicer. So we have 2, and then we would have a positive 2x, and then a plus 4. And then just an added thing, anytime you have a b value, you actually need to factor that b value out. And so you would add those parentheses and then divide by that b value. And so the correct way to write this is 2 to the 2, and then x plus 2. Lots of 2's. And then we have a big plus 5 outside. Okay, so all this is an equivalent way to rewrite that original function. Okay, so we are working with base 2. That's the parent function, not a transformation. And then we have a horizontal stretch or a horizontal compression by 1/2. And then we have a left 2. And then we have an up 5. Okay, remember that 5 is the horizontal asymptote. Domain is all real numbers. Here we do not have a reflection. We do not have a negative in front of the base. And so our range is still going to go from 5 to infinity. Okay, start by graphing the horizontal asymptote. You can use a dotted line. I've been using a highlighter. This is an invisible line, so I always want to remind you of that. And then my 1 away point on the y-axis, it hasn't been vertically stretched, so it's still going to be a distance of 1 away. It hasn't been reflected, so it's still going to be just a distance of 1 above the asymptote. The only thing we haven't taken care of is the fact that it's moved left 2, so we actually want to put it 2 from to the left. Okay, and so we've already taken care of the up 5 and the left 2. And so for our next point, it's going to be the base away. So a distance of 2. And so usually it would be right there, but because of the horizontal compression by 1/2, our distances between the points left and right are only going to be 1/2 instead of 1 each time. And so we are just going to take that point and move it in 1/2 so that it's right in the middle of those 2 points. And then you can connect them. If you wanted a third point, our next point, since our first point was 2 away, go over 1/2 and go 4 away. And so our points are all a distance of 1/2 horizontally. So up to the right and down towards the asymptote as you go to the left. All right, for this last example, they are giving us the graph, and we have to identify the equation, including the parent function. Okay, so the first thing I like to notice is I have a point here that's 1 away from the asymptote. And so find your next significant point to the right, which is a distance of 3 away from the asymptote. So because we have a distance of 3, that means I'm working with base 3, which means my parent function is 3 to the x. Okay, and so to identify the transformations, I'm seeing the horizontal asymptote has been moved down 3. Usually it's 0, and so if I see it at -3, that means it's down 3. And then my y-intercept that's 1 away has been moved left 2. Okay, usually it's sitting on the y-axis, so now if my 1 away point is there, not left 2, right 2. At the 2, right 2. And then it's still growing and it's still above the asymptote, so there's no reflections. We have that 1 away, 3 away, so no stretches or compressions, so only right 2 and down 3. So we're going to take that 3 to the x, and to move it right 2, we are going to move it, we're going to put a -2 in the exponent And then we're going to put a -3 outside the exponent.